so that it is saved. So so preliminary dates are 15, then 16, and, and then 20.
We can do exams until the 1st of March. So, because we also talked with who wanted to do it in April, and we told him that there was this possibility, and probably we will also try in these days. So we will see how it goes, but I think that this would be the best option for us.
Yeah, so I also write this in the email so that it is saved somewhere, and or maybe I'll first ask if it was possible to book these rooms, and or maybe I'll first write preliminary dates and times, and if it changes, I'll tell you. And by the way, concerning the beginning of January, will we already have some exams, or does someone want to come to discuss something now?
We have exams. If you are feeling best during those days.
Yes. So.
We can, in case, can we write you like during the first days of January to let you know if someone wants to come, like also to make you questions about something we studied and we didn't understand.
Yes, of course. But I'll be here anyway. For example, for lunch. So. So just should know if to come to this room or not.
Basically, I don't think because the lessons and today we don't have to come. If someone has the need, like we will let you know.
Okay. That's.
And I have a question about the Jewish problem. What do you mean by not more than 5 quadratic examples?
Probably I should have written that we can look for solutions of Laplace equation in polynomials. So U should be a polynomial of x, y, and z, and the degree of U is less or equal than 2. So in principle, we can write the general solution for any degree of this polynomial, but in this case, it is easier, and the answer is the same as for any other degree. Well, of course, it is always more convenient to work this way. But of course, a real part and imaginary part satisfy this equation themselves. So. Okay, so let us continue what we studied the last time. So it was a Sturm-Liouville problem. So we had an operator of this kind. Minus 1 over w u dx plus q of x plus 1 over w of x q of x And we want to we know that this operator has a simple spectrum, so it has infinitely many eigenvectors and eigenvalues, like Lfn equals to lambda n of n. And we can also find, just by studying this equation and the limit lambda to infinity, we can find that it has solution, and it is some quickly oscillating function similar to some sine function. And so we know that lambda n goes to infinity. And we want to prove that this fn's we can also so we know that this fn's are orthogonal, and we can also choose normalization in such a way that norm of each fn equals to 1. So in this case, the scalar product looks like this. And we have a theorem that this fn's form complete basis. So, namely, if we have some function phi, actually, maybe the can we can we can a little bit simplify this restriction, but I'm not quite sure. To be on the safe side, let us say that this is this function should be in the domain of our operator L, so that we can act on it and yes, so this section is defined. Because in principle, I don't know if you can simplify it using integration by parts. So let us consider this case. So this function should be, for example, twice differentiable. So in this case, if you consider Fn, which is the projection to the first n vectors, it is a sum from k equals to 1 to n, a scalar product of phi with fk's, and let us denote remaining part by delta phi, is phi minus phi n. So if we define this difference, then a limit from n goes to infinity of delta phi n equals to 0. So the norm of delta phi. This reminder, well, let me use this notation better, because delta is Gaussian.
On the scalar product inverted, because
No, I've normalized them in this way.
that one. Yes. So fk phi because
Yeah, you're right. Thank you. Yes. So it is actually quite simple, because we can check that. So it is a kind of decomposition. we can write it as phi equals to phi n. So it's proof. So phi equals to phi n plus delta phi. Mm, mm. Questions? Uh, Maybe let us use such. Mm, mm. So mm, so we can write this decomposition, and we also noted that scalar product of this phi n and delta phi n is 0. So if we now compute the following object, like phi l hat phi, then mm, it will equal to um, phi n l hat phi n plus delta phi n l delta phi n. So and now, so the idea is the following: we know that the left-hand side is mm, some fixed number, and in the right-hand side, it is some combination of coefficients of this phi multiplied by lambdas. But this lambdas go to infinity. So if it remains finite, it means that coefficients in front of very high eigenfunctions are small. And if you try to write it in a formal way, we do like this, and now try to estimate the right hand side. So we can write it as so phi l phi minus this this part what equals to delta phi n l delta phi n. But this is greater or equal than lambda n plus 1 times times the norm of delta phi n. Because we removed all the contributions with smaller eigenvalues. We removed so phi n is phi and without first n eigenfunctions. So we have this restriction, and now divide by lambda n plus 1, and we see that delta phi n is less or equal than what, 1 over lambda n phi l phi. And here we have some from k equals to 1 to n. Maybe let me split the sum into two parts. minus sum of k equals to plus. And here we have a lambda case times coefficients lambda case fk phi absolute value squared, and it is greater or equal than this. So I have split this this sum into two parts. So this part corresponds to a negative eigenvalues. Uh, hmm? No, it's phi n. N minus plus 1 to n. So the first sum is the first sum gives positive contribution. The second sum gives negative contribution. So we can remove this, and it will still be an equality. So it is so we can write that it is less or equal than 1 over lambda n phi L phi minus sum from k equals to 1 to n minus lambda k fk phi. So, and it is greater or equal than delta phi n, delta phi n. And so this is some constant. It does not depend on n. And this goes to 0. So the end of proof. Yes. Thank you.
And the second part is that they are definitely bigger than 0 from 1 and minus because lambda n goes to infinity, right?
Yes.
So you can, okay.
Yes, because for high eigenvalues, this part dominates. And
As we saw in the last lecture.
yeah. So, any questions about this? Oh, but let us now look again at the Legendre polynomials. So it is easier to use this Rodriguez formula as the definition just for now. And a scalar product is so originally it was integral of sine theta d theta, and it can be written as just integral so fg equals to integral from -1 to 1 f bar of x g of x dx. So and it is easy to check. So I would like to see this orthogonality. So we know that there are solutions of that second order equation of Sturm-Liouville type, and so they should be orthogonal. Let us check this. So it is easy to check the following, that x that all monomials with n less than L are orthogonal to Legendre polynomials for n less than L. So because we can just integrate by parts. So is it obvious? So, because if you consider the integral from -1 to 1 dx x xn dl over dxl x squared minus 1 dx, it equals to the integral from it equals to xn to power l squared minus 1 dl minus 1 over dx minus 1 x squared minus 1 power l from -1 to 1 minus a integral dx n x minus n minus 1 dl over dxl x squared minus 1 l minus 1 power l. So this boundary contribution vanishes, and we can do this iteratively, and we will be left with the integral over dx dx l minus n over dx l minus n x squared minus 1 to power l, and another integration by parts and give just 0. So the consequence of this is that even if you don't know anything about this Sturm-Liouville theory, we can just ask, we can just perform a Gram-Schmidt procedure with this scalar product on the unit interval and find polynomials which are orthogonal with the scalar product. They will be Legendre polynomials, like in particular, integral from -1 to 1 of dx so x squared over 2 minus 1/2 equals to what? Equals to x squared over 2 minus 1/2 integral from -1 to 1 equals to 0. So this is p2 of x.
The last part,
Mm-hmm.
just to know, should there be some constant?
Yes, like and factorial, I think. -1 to power n. But it is 0, so
Yes, yes.
it is. And if you want to compute the norm of L's Lagrange nth Legendre polynomials, then we can just take the highest term So if you say that PL of x equals to some CL x to L plus something, then norm of Legendre polynomial equals to scalar product of x to power L with PL. We can integrate it by parts, CL. So we can again integrate it by parts, and it will be what? It will be integral of minus 1 to power L CL L factorial and integral from minus 1 to 1.
On the calculation of
X cubed over, sorry, yes, minus x over 2. Yeah, sorry. So and it's orthogonal to P1, which equals to x, just because one is even and another is odd. So and here we have x squared minus 1 to power L over 2 to power L L factorial dx. Well, I don't want to compute this now, but it should be easy. We should change the variable such that integration is from 0 to 1, and this will be some beta function, which is expressed in terms of factorials, and the final answer is that it is 2 over 12 plus 1. So is it fine? So this should be done explicitly, but so to do this, we need to know that integral from 0 to 1, t to a minus 1, 1 minus t to b minus 1 dt equals to beta of a b beta function, which equals to a gamma function, gamma of a and gamma of b over gamma a plus b. So if we use this, then we can compute this integral. Maybe there can be some other way to do this. I don't know. So is it okay? So now, so this Legendre polynomials they have also some other properties that follow, for example, so either from their generating function or from orthogonality. So, for example, we can ask what happens if you multiply multiply them by x. And to study this, we can notice the following: that p n times x pl it equals to 0 when n is less than less or equal than L minus 1. Just because uh, uh, ah, just because we can well let me first make a simple statement. So maybe let me write it this way: x Pn scalar product with tail is 0 when n is less or equal than L minus 1. L minus 2, sorry. Because this is a polynomial of degree at most L minus 1, and all such polynomials are orthogonal to PL. So it is one statement. Another statement is that we can rewrite it like this: Pn x PL. So we move this x to this PL, and this equals to 0 if you look at it in this way, when L is less or equal than n minus 2. And combining the statements together, we see that the only option for this expression is to be alpha L P L plus 1 plus gamma L PL plus beta L plus gamma L PL minus 1. So, and I don't remember exact formula for these coefficients, but they can be derived, for example, from comparison of the highest terms of these polynomials. Because if we compare coefficients in front of xl plus 1, xl and xl minus 1, it should be enough. So, and this is the same for orthogonal polynomials with other measures as well, because here we used only orthogonality. So any questions about this? So let us now think about the following question. So for now we obtained this polynomials from some expansion of solution of Laplace equation, but we are not quite sure that those are all possible solutions of that equation. So let us now try to verify this. So again, our equation is in this case this one. So minus d over dx x 1 minus x squared d what do I try to use, maybe sorry, psi over dx equals minus lambda psi so since this psi is irregular, we can expand it as a Taylor series. So we can say that psi is equal to let me first rewrite this equation a little bit. So it can be written as x d over dx squared plus x d over dx psi. Maybe let us write it like this, minus lambda psi. And this remaining term with second derivative of psi. We can write it as d2 psi over dx squared. So it is a more convenient form for our purposes. And we can now say that this function is definitely regular around 0. So we can write it as a Taylor series. So psi of x is a sum of Cn x to the power n from n equal to 0 to infinity. So let us substitute it here. This equation gives us so who can tell the formula for the left-hand side? So what happens if we act with this operator on our series? What happens if we act on xn? Mm-hmm. Mm-hmm. Yes, thanks. And in the right-hand side, it is obvious. It is a sum from n equals to 1 to infinity c n n minus 1 x n minus 2, right? So if we now compare these formulas, so we can rewrite this right-hand side as a sum from n equals to yes, thank you, from n equals to 2 to infinity c n minus 2, so that powers of n are the same, n plus 1, x to the power n. So if you now compare these parts, then we see the following formula. So c n plus 2, n equals to 0 to infinity n plus 2. Sorry. So we see that Cn plus 2 equals to Cn. Yes. Sorry, I missed this. Yes. So we have this formula: n plus 1, n plus 1 minus lambda. So and there are two options. So this recursion can of course be solved, and we have two options. When a lambda does not equal to some l plus 1 for l integer, then all these coefficients are non-vanishing, and when we take the limit n to infinity, that c then we say that Cns behave like constant. So they behave like O of one, and if you want to be more precise, we can write that they behave like some constant one plus some alpha, which I don't remember precisely. It can be obtained. I think, and it means because this ratio of Cn plus 2 over Cn tends to 1. So it means that, and this estimation is not even needed. So the main thing is that the radius of convergence of this series is 1, which means that it develops singularities at one of the ends. So. And also, there is maybe a little bit tricky point to find where the singularity is, but since since this asymptotics is just one without any phase factor, we can find from complex analysis or just from common sense that the singularity is placed precisely at x squared equals to 1. So it has singularities at both 1 and minus 1. So it behaves like so. It starts normally, so it can be the even or odd polynomials, probably has some oscillations, and then go to infinity at 1 and at minus 1. So this is what I demonstrated in the general case for this polynomial having zeros at the ends of interval. So so in our case, the only possibility is to say that there exists such some L and that lambda equals to L plus 1. Oh, so I wrote L integer. Better to say that it is greater or equal than 0, but actually there is a symmetry. So this expression is positive or is negative for all integers, and it's symmetric for L and minus 1 minus L. So. So, in this case, we will have C L plus 2 equals to 0. C L plus 2 equals to 0. So, and so all CLs for L greater than all CNs for N greater than L equal to 0. So, and we recover precisely polynomials.
Because the first CL is 0
so we should say that here we have two occurrences for even coefficients and for odd coefficients, and one of them should be 0 just I would say from the very beginning, because otherwise, because they will not have a chance to vanish due to this numerator. So there will be no such n in this sequence if we jump by 2. And another series, all polynomials are either odd or even, and it follows from the equation because it commutes with a symmetry operator without with reflection. So there should be also eigenvectors of this reflection. Uh, and if you consider only this remaining half, they should also terminate at some number, because otherwise they behave as constant and produce singularity. So, is it fine? So, this way we see that all these polynomials are actually all solutions of this Sturm-Liouville problem. There are no other cases. And, mm, So, we can also write the general formula for these coefficients, because we can solve this recurrence relation. So, actually, do I want to write this? Mm-hmm.
We want that the solution we find has no problems at the boundary, so at 1 and minus 1.
Yes.
So we want that its power series has coefficients that are convergent.
Yes.
And so they go to 0. So for the first part, when we suppose that lambda is not at times plus 1, we found the Cn that behaves as 1, as a constant. So we cannot accept that solution. So
Yes.
we suppose that lambda is of that type. And then we can conclude that if it is of that type, all the CL plus 2, CL plus 4, and so on are 0, and the others, so the CL plus 1, CL minus 1, CL minus 3, must be 0 since the start, because if they were not, they would go, we would have again a series that has not converging to 0 coefficients, right?
Yes, precisely.
And for this reason, we have only odd or even polynomials.
Yes. And it's expected from the very beginning, because we know that this operator commutes with a reflection operator when this psi of x equals psi of minus x. And this reflection operator is, of course, self-adjoint. So even if we don't need to diagonalize it separately, the eigenspaces of this L hat should be also eigenspaces of reflection operator. So all solutions should be order or even. Uh, and by the way, concerning this general phenomenon, so we see this recurrence where we have some quadratic polynomial in the numerator, some n in the denominator, and some other linear polynomial in the denominator. And there is a function which describes all these classical orthogonal polynomials. Well, in general, all solutions of equations of such kind which can be written analytically. And this function, so it is very useful. So this function is hypergeometric function of A, B, C, and Z, and it equals to this to such series from maybe let me just write its coefficients. 1 plus AB over C Z plus A plus 1 B plus 1 over C C plus 1 2 factorial Z squared plus and so on. So that if you denote this as a well, Cn denote them dn. Such that dn over dn plus 1 dn over dn minus 1 equals to maybe dn plus 1 over dn. Better try it like this. Equals to a plus n, b plus n over c plus n, and probably n plus 1. So it's hypergeometric because geometric series is when this this ratio is just constant or 1. And hypergeometric is when it is a rational function of n. So this number 2 stands for 2 a and b's, to the degree of polynomial in the numerator, and this number and this one stands for the number of polynomials in the denominator. And so it has some nice properties. So, for example, you see from this formula that this and this, and that in principle this Legendre polynomials can be expressed in terms of this f to 1. So let me tell also another very similar story about the other part of Laplace equation. So not Laplace, but kind of a Helmholtz equation. So we know that Laplace operator in d dimensions is what it is dr squared plus 1 over n minus 1 over well, maybe better to write it in 1 and 2 and in 2 and 3 dimensions. So Laplacian in d equals 2 equals to 1 over r squared r dr squared plus Laplacian of phi over r squared. And eigenvalues of this Laplacian of phi are minus m squared. So in 3 dimensions, it is 1 over squared r dr squared plus r dr plus Laplacian of theta and phi over r squared. And the eigenvalues of this Laplacian are minus l plus 1. So in principle, what we want to do now is to diagonalize this radial part, because we already know that. Here we know that the eigenfunction of this angular Laplacian is some function of r. So we want so Laplacian on psi with some indices, like let us introduce some index a, maybe index k. Km equals to minus k squared psi km. And so we want this function to be eigenfunction of the full Laplacian, and also the eigenfunction of this angular Laplacian. So minus I dr d phi psi km equals to m psi km. This is for d equals to 2. And for d equals to 3, like delta d equals to 3 psi km klm. We want it to be again eigenfunction of this Laplacian psi klm with what? With also this equation satisfied. And it should be also eigenfunction of this operator. So minus I dr d phi. So so we can do this because these operators are self-adjoint and they also commute. And we can check that Laplace operator can have only negative eigenvalues because of integration by parts, like integral of f bar d over dx squared f equals to minus integral df over dx squared. So eigenvalues of Laplace operator are negative. So now, since we already diagonalized this angular Laplacian, we can replace it with some number. And this equation looks like, so for d equals to 2. For d equals to 2, it tells us that 1 over r squared r dr squared plus minus m squared over r squared equals to minus k k squared acting on psi equals to minus psi km equals to minus k squared psi km. And for d equals to 3, it is a very similar equation. Right? So we can now introduce the new variable. Let us introduce a new variable x, which is equal kr. So in terms of this variable, we can write the first equation like r dr squared plus r squared minus m squared psi km equals to 0. And for the second equation, so you see that this kinetic term is a little bit different. It contains this extra RDR, and it can be removed by the following procedure. We can divide this. So let me think. We can multiply this psi by square root of r. So we can check that the following equation holds. So r dr squared plus plus r squared minus L plus 1/2 squared acting on, sorry, it's not r, it's x, and here it is x. X dx, x squared, square root of x, psi in k L m equals to 0. So it happens because this happens because if we act with x dx, x dx squared on square root of x psi, when we act for the first time, it gives x dx on 1/2 square root of x psi plus square root of x x dx psi. And when we act for the second time,
So there is also an x in the numerator of the first. When we have 1/2.
sorry. Yes. 1/2 square root of x psi. So yes, of course. So when we act for the second time, again, we can act here, and it will give us 1/4 square root of x psi plus the term when it acts on psi, it is 1/2 square root of x x dx psi. So we have such term coming from here, plus 1/2 square root of x x dx psi. And we have the last term with second derivative, plus square root of x x dx psi x dx squared psi. So in total, it gives us the following, that 1/square root of x no, why?
Because we have the square root of x times x. So gives x to the 3/2. Then we derive and then multiply by x. So not 1/2, but 3/2.
No, but why we so we act only on this x. We don't touch this one because we want. So this is kind of scaling operator. A monomial is the eigenfunction of this, and it is nice because of this fact. So we see that 1/square root of x x dx squared square root of x psi equals to precisely what we want. It is x dx squared plus x dx plus 1/4 times psi. So if we now look at this expression, and we can also write that L plus 1/2 squared equals to L plus 1 minus plus 1/4. So if we substituted this relation and this relation here into this equation, we see that psi KLM satisfies this one. So it is essentially the same. And and the summary of this analysis is that we need to solve this equation, which is called Bessel equation. And this Bessel equation is this one, x so x dx squared plus here this coefficient can be either integer for two-dimensional Laplace or half integer for three-dimensional one, and so it is better to consider this equation for arbitrary value of this coefficient, probably even complex number. So this is x squared minus nu squared acting on psi. Let us write this on Bessel notation. G nu of x equals to 0. So this is a Bessel equation. J nu is a Bessel function. So is it fine? So we can now try to do the same. Namely, we can try to find solution of this equation as a power series. And to do this, let us look at the asymptotics when x goes to 0. So when x goes to 0, then we have approximately x dx squared minus nu squared j nu equals to 0. It means that j nu should behave as x to power plus minus nu. And since we have this freedom, it can be either positive or negative power. We can choose one sign, so we choose this upper sign. And find G nu in the form, so it is sum from n equals to infinity to, from n equals to 0 to infinity, G nu of x over 2 to power nu plus 2n. I write here 2n because we see that this equation has the same property that this operator does not change power of x, and this one raises it by 2. So it's n from 0 to infinity Cn. So now let us substitute it into the equation. So again, these two terms, x dx squared minus nu squared, give us, so let us write this from n equals to 0 to infinity. So these terms give us nu plus 2n squared minus nu squared, x over 2 to power nu plus 2n cn. And here, and plus sum from let me maybe shift the summation coefficient immediately. So we multiply it by x squared, and I want to say it is a sum from n equals to 2 to infinity. C 4 C 4 x over 2 nu plus 2n C Cn minus 2 equals to 0. N minus 1, sorry, because because um, I use even shift, so the shift is labeled by n. So are there any questions about this recurrence relation?
Because we have just written the power series with right? So
Yes. So sorry, from n equals to 1 to infinity. So this recurrence gives us, so if you open these brackets, we see that Cn is then equal to Cn minus 1 times, what we have here? We have here 4 nu n, which is, mm, so this 4 will be cancelled by that 4. Nu n, and we also have n, that 4n squared, which survives, plus n squared here. So here is this recurrence. So we can write a solution of this recurrence. So Cn equals to 1 over n factorial gamma of nu plus n plus 1. So gamma is a gamma function, like gamma of x plus 1 equals to x and gamma of x. So so having it is some formula. It's not normalized by 1. It's normalized in such a way that coefficients have some a nice simple formula. So it tells us then that the formula for solution of this equation is the series n equals to 0 to infinity x over 2 nu plus 2n 1 over n factorial gamma of nu plus n plus 1. So for example, if you take j0 of x, it equals to sum from n to 0 to infinity x over 2 to power 2n 1 over n factorial squared. Oh, sorry. I missed here the coefficient -1, and because it was sum of these two terms, and so they were in one side of the equation. So it is -1 to power n here, and here we also have -1 to power n, and here as well. So it is some funny series. So it's like some sine function or maybe like exponential, but with n factorial squared. So we see the series converges super fast. So it is a function defined in the whole complex plane. So, and this Bessel functions look like this. So J0 is something of this kind. Oh. This is J0. And J1, so it starts from the first power of x, which is something like this. And J2 is something like this. And they are nice special functions. And if you want to use them to solve, to find Laplace, to find eigenvalues of Laplace operator in some disk or in a ball, we should solve an equation like J nu of kr equals to 0. Find such so we need to find such k kns to find eigenvalues of Laplacian in disk or in a ball. So in r theta phi, when r is lesser or equal than r, or r phi also. So it's like for the problem on the interval, but now it is in the radial coordinate. We need to satisfy this boundary condition that eigenfunction of Laplace operator vanishes on the boundary. So we can scale this. We can scale the argument of Bessel function so that its zero is precisely on the boundary. So we can write that this kns equal to 1 over r some u nu n position of zero of the Bessel function. So this zero is u01, this zero is u02, this zero is u03, and so on. And here we have also some zero, u11, u12, and so on. So, are there any questions about this? So is it like everything clear, or everything is unclear? Okay. Okay.
The part about Legendre polynomials was just to show us a technique that now is also useful to solve the Laplace equation, or are they connected in a heavier way what we are facing?
No, it was not only to show the technique. It's actually a little bit different, because here we needed to have this quantization condition for series to be convergent, and in this case it is always convergent. Actually it was a double purpose computation. The first was to justify that we have only Legendre polynomials and that we are not missing anything else. And also to see this phenomenon, like how a solution of this spectral problems usually work. And also, of course, it is a bit similar to that equation. So. These equations, these are all equations, can be obtained by some reductions of hypergeometric equations satisfied by this F1. So I don't remember precisely what are the coefficients. Probably I can write something wrong, but it's easy to find it. Also, so we see that this Legendre polynomials can be expressed in terms of hypergeometric function. We can also introduce hypergeometric function f01, which will be, so it is just a function of c and z, and it will be 1 plus 1 over c, z plus 1 over c, c plus 1, 2 factorial, c squared plus plus and so on. And if we introduce such function, then see immediately that it is the same series as for a Bessel function. So. So this recurrence relation does not have a numerator. So it can be obtained actually in the limit when z goes to 0 and the a and b go to infinity. So. But the general idea is that if you want to study some special function, then we can start from just writing its series. And it is so it is in some way fine if you want to study this special function around 0 when this series works fine, but the next step should be usually to try to write some integral representation, because if you have integral representation, we can go to different domains and study asymptotics of this function in, for example, for x goes to infinity. So here it is a little bit unclear what to do when x goes to infinity. But if you obtain some integral representation, then it will be much easier. So, and so. So to do this, we can use the following formula. That 1 over gamma function of s equals to the integral over the following contour. So it is 0. That is some branch cut which goes to minus infinity. It has some name, I don't remember precisely this name. So there is this integral over this contour, which we denote by c. And the integral is of 1 over 2 pi I e to the power z dz over z to power s. So when s is non-integer, then this integral is really over this contour, and when s is integer, when s in z, then there is no then this z to power s is a single valued, and we can say that it is just a integral around 0. So 1 over gamma of s. It's just 1 over 2 pi I, integral around 0, e to z dz over z to power s. And if we want to compute this, we need to expand the exponential as a series. So it is 1 over 2 pi I integral sum of z to power n over n factorial 1 over dz over z to the s. So the only term which survives this computation is the one with n minus first power, and integral for this term is 1 over n minus 1 factorial, s minus 1 factorial. So, and it's actually a simple way to remember this formula, because you can check it for integer n. So this streak. And it's different integral representation. So it's for 1 over gamma of s, because the standard representation is for gamma of s, which is integral from 0 to infinity, e to minus t, t to power s minus 1 dt. So in the standard one. Well, actually both of them are standard, but maybe this one is used as a definition of the gamma function, and this is a little bit more advanced. So, by the way, have you seen them before?
The definition of the gamma function, not the inverse. So not the one defining the with the continuity.
See. So actually, well, there is some part of humans' knowledge about this gamma functions, beta functions, and so on. So maybe so there are some non-trivial relations, like if this true, why this one should be true, and so on. And all this actually follows from this formula for beta function expressed in terms of gamma function. So there is one identity which we should verify. Probably I should have thought about this and tell this. But it can be found somewhere. So if we know that identity, then we can just substitute something like a beta of s and 1 minus s, and use a relation for the product of gamma of s and gamma of 1 minus s. So this integral can be shown to be equal to gamma of something like 1 minus s multiplied divided no, multiplied by sign, because the streak, when we integrate such a expression as a jump on this branch cut, it differs by e to the 2 pi I e to the 2 pi I s. Well, maybe it's not a good idea to try to explain it without proving, but let's just try this formula and use it. So at least we know that if we are talking about integer Bessel functions which are valid for d equals to 2, then this is the proof of this formula. For integer s, it is just a statement about a Taylor series for the exponent. So when we have this integral representation, we can use it to write this 1 over gamma. So j nu of x is the integral 1 over 2 pi I, the integral over this contour e to z dz over z to what? Nu plus n plus 1. Sum over n from 0 to infinity, then 1 over n factorial minus 1 to power n over n factorial r over 2 to power nu r over 2 to power 2n, and well, that's all. So now we can combine several terms. So it's 1 over 2 pi I integral over this contour C e to power z. Then we combine the z to power nu with this r over 2. So it is r over 2z to power nu dz over z. And let us combine this to one exponent. So it is e to minus r over 2 squared z inverse. And now let us say that our variable z equals to some 2 over r, some variable z tilde. So under this change of variables, this becomes 1 over 2 pi I integral over this contour e to r over 2 z minus z inverse yes, thank you. Because for x over 2, and here we have dz over z z nu plus 1. Well, we can just change this variable. So we have this nice formula. So now, what can you say about this? So there are several questions about where is So when nu is different from so when nu is non-integer, then solutions of Bessel equation. So this is second order equation, so it has two solutions. And so the solutions are j nu and j minus nu. They have different asymptotics, so they're independent. So there is another case. So when nu is integer, uh, we can actually close this contour. So this function becomes single valued, and we can introduce a new function. Like we can say that z equals to e to I phi, and this g n equals to the integral over d phi from 0 to 2 pi e to the ix sine of phi minus I n phi. So d phi. So since this function is antisymmetric and the placement phi to minus phi, this integral can be written as an integral from 0 to pi cosine of x sine of phi minus minus n phi. And we see that in this case Gn and G minus n, let me think, so in this case Gn of x equals to something like minus 1 to power n G minus n of x. And so enably it seems that we don't have a second independent solution, but this problem can be resolved in principle. We can define a function like y nu of x, which is j nu minus minus cosine of pi nu j minus nu over sine pi nu, and then take nu to n. So it will be a well-defined function. So it is one way to solve the problem, one way to find another solution of this equation, and another way is the following. So we see that actually, let me think. So we see that in principle there is some other way to close this contour because this function in the exponential z minus z inverse goes to 0 in both in two cases. One case is when z goes to minus infinity, and another case when z is a small positive. So in principle, we can consider so we can consider another way to solve this problem, which is this one. We can define Hankel functions. Probably maybe I don't remember who is the first one, who is the second one. So we can define them as such contour integrals. So we don't go back to infinity, but we instead go to this point and terminate integral there. And the integrand is the same. E to x z minus z inverse dz over z nu plus 1. And we can define the same function, the same integral over another contour. So, and since they are kind of integrals over half of this contour, and there is a relation like h nu 1 equals to j nu plus I y nu. So learn this relation. And there is also the last nice part. This is this happens when we want to study the two-dimensional Laplacian, and we have this integer news. But for d equals to 3, these news are a half integer. And we call these functions which appear in this case, so namely this psi, which is Bessel function divided by square root of x, is called as spherical Bessel functions. So they are defined like this: j L of x equals to 1 over square root of pi over 2x, and j L plus 1/2 of x. So that it satisfies this equation, this radial part of 3D Laplace equation. And a nice thing is that unlike this usual Bessel functions for arbitrary L's, these ones have explicit expressions. And this explicit expression looks like this. J of x equals to minus x to power L, 1 over x d over dx to power L, acting on sine of p, sine of x over x. So if you look at this formula, then so these Bessel functions have some properties uh, like asymptotics at infinity, for example. So this asymptotics at infinity can be analyzed starting from the integral representation. You can compute it using saddle point method, for example. But if you believe that this asymptotics is similar for all else, then we can just look at this JLs for half integers and see that and this one behaves like a sine of x over x. So it means that original Bessel function before division by square root of x behaves like a sine of x divided by square root of x. And also if we want to see the other functions from this Bessel family, we can just replace this trigonometric function by something else. So if we want YL of x, then it is maybe with some sign. Don't remember precisely. On the same formula with cosine, maybe just no, just cosine of x over x. If we and these Huntley functions correspond to exponentials, so h1 2 of x L of x equals to e to I x over x, and this operator acting here. And what e2 plus minus ix. So we see that this function, and well, I don't have time to prove this identity, but it is actually quite simple. It just follows from the series representation, because we have here n factorial times gamma of n shifted by some half integer number. And if you write gamma of x plus 1/2, then we can write that it equals to gamma x, maybe x plus 3/2. We can write that it equals to x plus 1/2, gamma of x plus 1/2 equals to, and so on, x plus 1/2, and so on, 1/2, gamma of 1/2. And this gamma of 1/2 is square root of pi. So in total, it equals to 2 to minus x plus x minus 1, gamma of 2x plus 1, 2 factorials. It means a product of all half integer numbers up to this one times square root of pi. There is this identity, and there is also another identity that that n factorial equals to n factorial equals to 2 to minus n times 2n double factorial, which means product of all even numbers. And There is also the last identity that if we multiply 2 2x plus 1 with 2x plus 1 double factorial times 2x, well, 2n plus 1, 2n double factorial, it equals to 2n plus 1 factorial. No, yes, it's true. Maybe it was better to use n here. So, because otherwise we cannot reduce it to 0. So, and if you do this exercise, you can recover here this this series for sine of x over x, but it will differ only by some finite numerator, which can be precisely obtained by the action of this operator. So. And actually, you could see such functions if you solve the problem about grand function of Helmholtz equation in I think in 3D, maybe in 5D, because these grand functions were precisely not Bessel functions, but modified Bessel functions. And by modified, I mean that we can consider this function as a function of a purely imaginary argument. So in this case, it becomes hyperbolic sine, it becomes hyperbolic cosine, and the problem with them is that, for example, this hyperbolic sine is regular at 0, but it explodes at infinity. So some natural choice for this functions of imaginary argument are this modified Bessel functions for 0 at 0, and a modified Hanke function at infinity, where we can, when one of the exponential is decaying. So the function which you saw in that in one of the problems was precisely this one. So it was e to minus mr. In 3D, it was e to minus mr over r. And in higher dimension, it contains several terms which come from this derivative. So, and you see, if you so if you try to find zeros of this spherical Bessel functions, then in most cases there are some transcendental numbers, because you need to find zero of equation which contains sine of x plus some cosine of x divided by x. So it's clearly transcendental, but the asymptotics when n goes to infinity, or when x goes to infinity, so the leading asymptotics is defined by this sign. So and we see that this function has infinitely many zeros, and general pictures are of this kind. So, are there any questions on this? Okay, if no, then let's go for lunch and resume in 1 hour.